Welcome to this video where we will be going over the solutions to the embedded activities in the Part A lecture notebook for the fourth module on computational applications. The first activity is to play with the bisection algorithm. I have several notes here about how you may want to create additional code cells below as you work through this activity. You will probably also need to adjust the A, B, and plotting parameters, xmin and xmax, in order to capture the root for the functions you are playing with. Because if your root in the example that you happen to look at is 100, then you need to set up the problem in the graph and everything so that you actually are centering all of your activity around the computations around 100. It is okay to show examples that do produce errors. This is in fact encouraged as long as you explain the errors, but you should also show results that do not produce errors. And I'll actually go ahead and do that in this first part of this activity. This activity is broken up into several parts to try to really parse it out. It's not meant to be too bad. You'll see actually how little I'm asking you to do as I work through this solution. So the first thing to realize is whenever I say sum in any activity, that means at least 2. So in this first instruction, when I say test a plot bisection function on some lambda functions, you need to pick at least 2. These are functions of your choosing, so you can't reuse the functions I'm using. Now you can modify them, but they gotta be your own. You've gotta change them somehow. So I'm gonna show some that I'm messing with. I would appreciate if you didn't just use the ones I showed in the video. You should use your own, some variant of it at least. And then you need to, for each of these, you need to do it with and without widgets. So I need at least 2 lambda functions, and then with each one, I should show the plot bisection with and without widgets. So let's go ahead and start with widgets because I don't believe I showed any examples above without widgets. So I can just copy and paste, let's say, this code cell. And I'm going to do it here in this because I'm going to show the, I'll do it with widget and then without widget next. So here's with a widget. Now, I don't want to use this function. I want to change it somehow. So I'll just change this to, let's say, cosine of x cubed minus x, and then I'll subtract off 2 times x. Now, if I do this, I am pretty sure that I'll get an error right away. So watch what will happen. Like I'll run this, I won't get an error right away because I have to run interact to generate the plot, but watch what happens when I run interact. I get a value error. Now, this is actually producing an error that was written in the compute bisection function, right? And it's doing the right thing because the A and the B values are not correct for where the root should be. Look at A is 0.5 and B is 1.75. And you said, well, what was going on? How would I know where to set this up maybe initially? So you could look at this, say, okay, xmin 0, xmax 3. Let's go ahead and create like an array of x values. And let's do it from, let's say, -5 to 5 and use 100 points. So I'll just kind of make it like this. So this is just to create some initial investigation on your side, like how would you determine what would be some reasonable values to search for a root. Now, let's go ahead and create a figure. And in that figure, let's plot x, and let's actually plot, right, this function evaluated there. So let's go ahead and do this. I'm going to create a little lambda function, f equals that lambda function, and now I'm just going to plot f of x. All right, let's go ahead and plot. Oh, and maybe don't have a syntax error. There we go. Now here's this crazy function, right? We have a linear trend. It's kind of a funny function because I took -2x, right? And you can basically think of this as -2x plus what's on the left of it. And I'm basically taking a very oscillatory function and putting that around a linear trend. So you get this kind of funny looking function. And it has a root somewhere around, I would say, the 0 area. And it's all basically after you get a little bit to the right of 0, you're certainly always negative, and it seems like it's always positive if you get to the left of 0. So having an A and a B value that are maybe both positive at 0.5 and 1.75, that's probably the reason why I'm getting the value error. And in fact, it makes a lot of sense because I'm seeing that f of A and f of B are not different signs. They're the same sign. They're both negative in this case because I can see this from the plot. So just doing some quick visualization like this, where you just use a wider range of x values in your plot, can give you some better insight about how to fix the inputs for your plotting and running this algorithm. So I would say here, let's go ahead and plot, let's say from let's just go ahead and center it, -2 to 2. Let's let A go from -2 to, let's say, just, well, yeah, we'll go to like 1.52. And then we'll just have 1.53 to 2. Well, we'll have, yeah, that's fine. These will be, because these are just the initial values. But let's go ahead and set A to be, let's say, -2 in this case, the min value, or we could say -1, and let's say b to be 1, because that seems like it should capture the root that we see here. Now, if I run this again, right, and I see that a is set at -1, right, I can bring it all the way down to -2 if I want, but I'm going to set it back to its default value. Well, okay, I'll -1. B is set at 1. Oh, it's set at its min value because I wanted B to be 1 there. So let's go ahead and set B to be, let's say, like 0. Or we'll do 0.5 for the original one. There we go. Now B can be 1, right? This all makes sense now. The values we're setting are within the range of the min and max on our sliders. Now we'll run, hey, no error. And look, it split the difference of the two because it's positive and negative, and the bisection's working, and it's giving a root of 0. And you can explore, you can say, like, what happens if I go to like 5 iterations? And oh yeah, it's getting really close to where the 0 occurs, which seems to be close to maybe a little to the left of 0.5. And that would make sense why we were seeing an error before. So that's kind of it for one of these things. Now, that shows it with interactivity. What you should do as well, and maybe it's easier to actually add this above, so I'll create a code cell above, and I'll just go ahead and remove that code cell, is to do it without interactivity, you just call the function. And then you just pass in these various arguments into the function directly. And you don't use any kind of interactivity from a widget. So the easiest way for you to perhaps do this is you could copy and paste this material, these parameters in here. And it's nice to actually do this in an array. I'll just go ahead and type them out because I'll make some comments along the way about inputting these things. The arguments of plot bisection are keyworded, right? There's f, a, b, n, x, min, x, max, grid points, show final interval. So we don't have to do these in order, but it makes sense if you know the order to do this. So we could have f is lambda function. I'll go ahead and copy parts of this, right? The point is you don't want to copy the widget part. So, all right, because we're not using widgets here. You should only capture the actual input, the initial input. So here we go. That's going to create the function that we're looking at. Now I'll put a comma here, and then I'm going to press enter. All right, and I'm actually going to press, I'll do this one at a time so you can see it here. I'll just go ahead and go back to there. So if you have a lot of arguments, it's really useful in a function to list them vertically for ease, for readability. It's just ease of reference. It's just easier to see than listing out a bunch of parameters for inputs horizontally. And so as long as you have that comma there, it's just going to read to the next line. And the next thing is the a value. Let's say we started at -1. I need a comma, again, to go to the next one. It always wants to align up the, I'll show again, actually. Notice when I press the enter key or return key on your keyboard, it lines up the parentheses, but they don't have to be aligned exactly. So, it's interesting is if you have an argument here, if you write the next one there, if I have that next argument there and I press enter, look what happens. It aligns that with F. But if I press enter here, okay, well now I guess with that, those parens are lined up. So maybe that's the way to do it. Have the parens lined up and the parentheses lined up, and then just press enter after each comma without the parenthesis there so that you can get good alignment of these. But anyways, b equals 1, comma, enter. N equals, this is up to you. We saw like 5 iterations below seem to give a really good result, so we'll stick with 5. X min was -2, right? It's right there, -2. X max equals 2. Again, comma, grid points. I think 100 is probably sufficient in this case, and show final interval. And maybe here, let's just say true. And then if you generate this, notice there's no interactivity. We just generate one figure, and we're showing the final iteration where we're getting this approximation of the root. It's just kind of a busy looking plot. That's why I don't always like to show the final interval. So if you don't like it so much, like I don't really like the way the plot looks, I would maybe do false. And yeah, then of course, when you generate a lot of figures in a notebook, it'll give you some warning. You run this again, it goes away. There we go. That might have happened to you at some other point in the notebook when you were running it. So that's a nice looking plot. You see A, F of A. I don't have the subscripts on them because I'm not showing the final interval, but this is the final approximation of the root from 5 steps of the bisection algorithm. So that's without interactivity. This is with interactivity. And that is for one of the at least 2 lambda functions you should test. And I don't think you need to see me do a second one. You just need to do it yourself. Change these functions. And again, you might have to do some plotting and some investigative work to figure out good values of A and B and X min and X max. And then depending on that, you might change your grid points in order to get a nice smooth looking plot. So I'm just going to go ahead and move on to the next part of this activity. Again, you need to do at least two Lambda functions on that part. Notice that plot bisection does not have any tolerance parameters. When it calls compute bisection, it is simply relying upon default values for these parameters. So again, if we go look at the plot bisection, right, it's just calling compute bisection with FABN, which are the parameters here, FABN. If I go look at the compute bisection function, just for a reminder, here we go, it had default parameters for the tolerance parameters, tall interval and tall f. So since we're not setting these anywhere in the plot function that calls it, it's just using the default ones when it calls compute bisection. And you'd say, well, maybe I want in my plotting to see what happens as I change the tolerance parameters. So I'm asking in the activity to basically copy and paste this code. So I'll just do that now. Boom, copy and paste, right? And it's a long code, but again, all of this is just plotting down here. This is the whole computational part. It calls the compute bisection, and here's my plot. Now, what am I asking you to do? Create an improved plot bisection function. So you better change the name to improved plot bisection. Great. That has done this part of the instructions. This allows for all of the parameters in the compute bisection function to be set by the user. Well, f, a, b, and n are the first four parameters in the compute bisection, and the tolerance parameters are the next. And if I don't want to use default ones, I just want the user to define them, instead of putting them at the end, in which case I would have to give some default values here, I should put them here because, in fact, I should group all the parameters that are passed to this function together. It makes more thematic sense, I think, to do that. So I think it's a better design choice. So let's put those there. If you put them at the end, you're going to need to add default values or it won't work because I already start having some default values here. So now that at least adds these as parameters to this function, but they're not being used in compute bisection yet. Just because you're passing them in, they're not used anywhere in this code until you do this. There you go. I'm adding those tolerance parameters. Now they're being used. Those edits right there, changing the name of the function, adding these two parameters, and making sure you pass them to the compute bisection, that's all you need to do to satisfy this part of the activity. And then you run that code cell, right? You can just check it ran. So now I have this function. And now to finish this activity, you basically just redo what I was asking you to do at the beginning of the activity. Tested this function out, now the improved one, on some, meaning at least two Lambda functions, with and without widgets, and I say you should use the float log slider for the tolerance parameters, since we often vary tolerance parameters by orders of magnitude when we are testing an algorithm. So let's go ahead, and I'll show this with widgets first, just like I did before. I'll take this piece of code, I copy and paste it here, and now it needs to be improved plot bisection. And I have F, A, B, and N, where I should put the tolerance parameters naturally is here. They're keyword, you don't have to, but I'll do the tolerance, I think it was interval first, and then parameter, yeah, tolerance interval equals widgets.float log slider. All right. I'm just going to kind of put placeholders in there first, and I'm going to show you if you forgot about what's going on with the float log slider, how you would say, what are the inputs I should give for these? So if you forget, remember, you can always use the help function. And you could say, what do I do with this float log slider again? You look at help. You could go to the web page, you could go to the documentation, but you can also print it out here for ease of reference. You don't, just keep everything within the notebook for simplicity. You say, okay, I have these arguments, these parameters that go into this function. I need to give it a value, which is the position, the initial position of the slider. So what should we do? Well, let's go ahead and say value equals maybe 1e to the negative 4 for the tolerance interval. That would be an interval of length 0.0001. And maybe for the value of f, we'll say value equals 1e negative 5. We'll just do something like that. Now, I'm putting parentheses there because we need some others. Base of the logarithm scale, the default is 10. I want to use 10, so I'm not going to even set the base because I want to use the default value. The min and the max are the minimal position of the slider in the log scale, so it means 10 to the what power and 10 to the what power for the min and the max. So what should we do? Okay, I think for the tolerance interval, maybe I want to vary it from, 10 to the negative 7 to 10 to the negative 1. So let's say min equals negative 7, and I'm going to do some spaces here for ease of for making it more readable. Negative 7, and max is negative 1. So that goes basically 0.00, 6 zeros and a 1, or 0.1 if the max is negative 1. And then, of course, I have to set a step size, the step of the track. So I'm gonna step in whole orders of magnitude. I'm gonna say step is 1. Okay, so that's gonna step, from, like if you were at the max value and you were stepping down, you'd go from 0.1 to 0.01 to 0.001 and so on. That's what a step of 1 would be. For the tolerance of f, I think the min value should maybe be, let's say, negative 13. That's really small. You're asking for the absolute value of f to be close to 0, to be within 10 to the negative 13. So that's at like a 0.0, 12 zeros and a 1. That's really small. You're definitely flirting with kind of machine epsilon at that point. And let's say, you can maybe allow a lot of error, 0.001. That's a sufficient amount of error, I think, for being close to 0. And let's also step in orders of magnitude. Now, you could step in half orders of magnitude, which would be 0.5, but that's kind of up to you. Now that's it. I've changed improved plot bisection. I have my tolerance parameters set, and I can run this now. And I say show, I run interact. We say here's that initial 1. I can change the tolerance parameters around. I can go increase in. I can just run my interaction, right? So, you can say like, what happens if I go to like 100? So let's do like 20. 20 is the max end that I have. Is that right? Yes, 20 is the max end. So if I run that, right, it's saying the approximate is 0.46698. And that's with these tolerance parameters. But what if I change my tolerance parameters for my interval? It's 0.0001 here. What if I make that a little, just one order of magnitude smaller? Do I get a different result than 0.46698? I do, right? So that's showing the effect of changing the tolerance parameters. So again, this is one function. You need to do at least 2, and I also need to do it without interactivity. I don't think I need to show that here, because all you need to basically do is follow along with what I did here, except this should be improved plot bisection, and you need to make sure you have the tolerance parameters set, right? And you just do that here. So just make sure you're using improved plot bisection. I would do it up above. It makes it easier to copy it, the information. And you just kind of follow along. Put in an F, an A, a B, and again, you can, here, I'll line those up like that. Actually, here, this is the way to line it up. You set that, and then you have your A equals, your B equals, and your N equals, your tolerance interval equals, your tolerance F equal. I think you get the idea. You just fill in all the parameters that go into this function, and then just put in these values, like put in the lambda function here, put in your A, your B, your N, the tolerance values. You might start with 1e negative 4, 1e negative 5, or you maybe use one that you play around with the slider. It's up to you, but you have to pick one. These are static plots, and these are interactive plots. And then again, you repeat that for another function. That's all I'm asking you to do for that activity. So I think I'm just going to go ahead and move on to the next activity. And I'm just going to go ahead and remove this help function because it's printing a lot of information. There we go. Makes it easier to scroll. So the next activity is about implementing a bisection variant. I actually think in the interest of space, I'm going to create shorter videos. So this is going to be video 1. I'm just going to stop it here. And then I'm going to create other short videos for these activities. That way you can watch each video for the information to the solution related to each activity. So thanks for listening to this, and I'll talk to you in the next one.